What would you think if a comet seemed alive? Astronomers recently noticed one behaving as though it were taking slow breaths in the cold of deep space. This traveler, catalogued as 3I Atlas, is exhaling roughly 40 kilograms of water every second, and doing it far beyond the region where sunlight should have any power to melt ice. In the darkness, that kind of activity shouldn't exist. Yet telescopes keep recording the same impossible behavior. Scientists half-jokingly whisper that the comet is breathing. But behind that humor is genuine confusion, because nothing in our textbooks explains what they're seeing. And the puzzle doesn't end with water. Its tail carries nickel without iron, traces of cyanide, and isotopic signatures hinting that it may be billions of years older than our own solar neighborhood. While professionals debate in observatories, hobby astronomers on Earth have been spotting giant radio rings stretching across the sky, odd coincidences that fuel every kind of theory. October skies have grown crowded with alignments. Mercury here, Ceres there, and far away, Atlas gliding through them, all like an uninvited messenger. Every week seems to bring another riddle. Even the latest Blue Origin test flight, meant to mark routine progress, has left more questions than confirmations. Something is happening above us, and the answers are slow to arrive. So, for the next few minutes, stay with me as we piece together these strange new signals and the story of the comet that refuses to die in the cold. If you enjoy exploring the universe's mysteries as they unfold, remember to tap like and subscribe, because this is just the beginning. Imagine drifting 3 times farther from the sun than Earth ever goes. Out there, the sunlight is thin, more suggestion than warmth. Comets at that distance should sleep, their icy hearts locked in silence. Yet through the darkness, one begins to shine, spewing vapor into the void like a geyser on a frozen world. That is 3I Atlas, a visitor from another star system, a piece of alien chemistry wandering into our cosmic backyard. Its behavior breaks every rule we thought comets obeyed. The first hints came from NASA's Swift telescope, a satellite built to chase gamma-ray bursts, but always eager for new curiosities. When Swift turned its ultraviolet detectors toward Atlas in early 2025, it saw something extraordinary: a glowing halo of hydroxyl molecules surrounding the comet. Hydroxyl appears when sunlight tears water apart. It is, in a sense, the dying breath of water vapor. Seeing that halo means liquid molecules had just been broken. And Swift didn't find a trace, it found an ocean. Calculations showed that at a distance of 3.5 astronomical units, roughly 500 million kilometers from the Sun, Atlas was releasing 1.35 octillion molecules of water each second. That's about 40 kilograms every second, or the weight of a small car every minute, hurled into the void where no comet should stir. In our solar system, such activity begins only when a comet dives much closer to the Sun. Farther out, they freeze and wait. Even sunlight cannot reach deep enough to free their buried ice. Yet Atlas was erupting early, a rebel against the cold. Astronomers, of course, demand mechanisms. Could hidden reservoirs of exotic ice be evaporating at impossibly low temperatures? Is internal friction or trapped radiation warming the core from within? Perhaps the comet's spin focuses the meager sunlight onto pockets of volatile material. Or maybe, deep inside, unfamiliar chemical reactions are unlocking energy in ways we've never modeled. Each possibility is more radical than the last. And still, the data insist. This object is alive with motion. But water isn't the only thing escaping. Spectrographs have picked up cyanide, carbon dioxide, and most baffling nickel atoms without their usual partner, iron. Every new reading adds another layer of impossibility. It is as if the comet obeys physics written under a different star, with rules that our laboratories have never tested. To scientists, Atlas isn't simply a curiosity, it's a window, a fracture in our understanding through which we can glimpse what worlds beyond our own might be made of. The question haunting every observatory is simple yet profound. How can this be? When metals boil away from comets, they usually leave in pairs iron and nickel, inseparable companions born together in the furnaces of stars. Where one appears, the other follows. It's so consistent that astronomers use it as a reference point, a cosmic fingerprint. Then came Atlas. At Chile's Very Large Telescope, spectrographs captured emission lines blazing bright for nickel and almost none for iron. A separation that should be impossible. Nickel without iron is like seeing smoke without fire, or a footprint without the traveler. How could a comet pull that trick? Maybe, scientists propose, the environment where Atlas formed allowed nickel to bind with lighter, more volatile compounds molecules that evaporate quickly, while iron stayed locked inside heavier minerals. If so, sunlight would release nickel first, leaving iron behind. Another possibility involves exotic chemistry. In carbon-rich regions, nickel can join with carbon monoxide to form compounds that vaporize at low heat. If Atlas grew up around such materials, its nickel might be escaping through these fragile bonds, while iron remains trapped. Or perhaps time itself changed the surface. Interstellar radiation can cook a comet's skin for eons, transforming its top layers. Cosmic rays might have etched away iron, while leaving nickel intact, a kind of atomic weathering that hides the comet's true composition beneath a metallic rind. And then there's the most thrilling hypothesis. Atlas might simply come from a star system, whose chemistry is not like ours at all, an ancient place where nickel was common and iron scarce. Every comet is a fossil of its birth. If Atlas was born around an older, chemically distinct star, that difference is now written into every molecule it sheds. For now, every observatory keeps its eyes on this glowing messenger, collecting spectra night after night. Each image is a coin toss between reassurance and revolution. And so far, revolution is winning. Most comets wake gently as they approach the sun, brightening in a predictable rhythm. Atlas prefers drama. Its light curves refuse to follow the rules. At first it looked dull, a reddish smudge like countless icy bodies drifting in the outer dark. Then, as it drew inward, something flipped. Its color shifted violently toward green, a vivid, spectral green that cameras could not ignore. That hue comes from two culprits: cyanide gas and atomic nickel, both of which radiate strongly in the green part of the spectrum. Their emissions didn't rise gradually. They surged, outpacing even the inverse square law that governs sunlight's intensity. Some hidden switch had been thrown. Astronomers call this switch-on behavior, a threshold where dormant ices suddenly awaken. Below that point, nothing happens. Above it, the comet erupts. Atlas seems to have several of these triggers. Water first, then cyanide, then nickel, each unlocking at a different temperature, like a layered code inside a frozen machine. One model imagines tiny icy grains lifted off the surface by earlier gas jets. As these grains drift outward, sunlight warms them individually until they begin to evaporate on their own, creating a cloud of secondary outgassing. The effect compounds, explaining why Atlas brightens faster than geometry allows. Another theory invokes thermal fracturing, the cracking of ice and rock, as different materials expand at different rates. Each fracture exposes new ice, fueling fresh eruptions, a chain reaction of awakening. And still others propose exotic ices unknown in our system, volatile substances that ignite into gas at temperatures where common water ice would stay frozen solid. If Atlas truly carries these alien ices, then every eruption is a whisper from another chemistry, another world. Comets in our neighborhood, sometimes misbehave sudden outbursts, even self-destruction near the sun, but nothing at this distance compares. Atlas is alive where silence should reign. Its pulses of light feel almost intentional, like signals from a frozen mind. Each new observation tightens the tension. What will it reveal next? Every object in the sky tells its own story through motion. Atlas's trajectory is not a loop, but a hyperbolic orbit that enters the solar system once and never returns. It came from the deep galactic dark, borrowed the sun's gravity for a brief encounter, and will soon vanish forever. By tracing its path backward, astronomers found archived images, tiny dots of light captured years before anyone knew to look. When those clues were stitched together, the trail pointed outward toward the thick disk of our galaxy, a region filled with older stars orbiting on tilted, eccentric paths. That origin alone hints at an ancient lineage, a system forged when the Milky Way was young, its chemistry unrecognizable by modern standards. What we're seeing now, as 3I Atlas exhales into the void, may be a relic of a vanished star, a piece of cosmic archaeology gliding through our sky for a few short months. And through this wandering shard, we are reminded that our solar system is not the rule. It's just one local version of a much stranger universe. High above the thin plane of our galaxy drifts an ancient population of stars known as the thick disk. Their orbits are tilted, their paths puffed up above and below the Milky Way's bright ribbon, and their chemistry betrays a different era of creation. These suns are elderly, born when heavy elements were rare, forged in a universe still learning how to build worlds. When astronomers traced 3I Atlas's long, open trajectory backward through space, it pointed not to the young, metal-rich, thin disk where our sun resides, but toward that older realm. If that conclusion holds, this comet may have formed before the solar system even existed. Our sun is about 4.6 billion years old. Thick disk stars can exceed 7 billion. That means the ices now steaming from Atlas's surface could have condensed in a nebula that predates Earth, Jupiter, and the Sun itself. Chemically, that's staggering. The gas clouds that birthed those primordial stars contained far less of the metals astronomers speak for any element heavier than helium. The first generations of stars lived and died, scattering those heavier atoms into the galaxy through supernova. Each new stellar generation enriched the interstellar medium a little more, building toward the periodic table we know today. But Atlas comes from an in-between age, a time when the galaxy's chemistry was still sparse. In such an environment, elements like iron, magnesium, and silicon, the scaffolding of rocky planets, were scarce, while lighter atoms like carbon, nitrogen, and oxygen dominated, locking themselves into volatile ices. That could explain Atlas's chemistry. The overwhelming carbon dioxide, the strange ratios of metals, the high abundance of molecules that would vaporize instantly near our sun. It might truly be a chemical fossil, a relic of a younger galaxy with an emptier table of elements. Tracing its birthplace precisely, however, borders on impossible. Over billions of years, stellar encounters, spiral arm passages, and gravitational nudges scramble orbits beyond recognition. The comet's trail through space is a blurred memory. Yet even the possibility that it hails from that ancient stellar population is breathtaking. We may be observing a survivor from the epoch when the Milky Way was still forming its first stable worlds. If someday we could identify its natal cluster, one of the families of stars that formed together from the same gas cloud, we might uncover siblings. Other comets, perhaps even planets, ejected long ago and now scattered across the galaxy. Atlas could be just one letter in a message written across thousands of light years, waiting for us to learn the language. Comets are not just frozen debris. They are archives, tiny spacecraft launched by nature, carrying samples of the chemistry that built their home systems. And Atlas's cargo list is extraordinary. We already know about the water 40 kilograms per second streaming into space where no comet should melt. That was the first clue. But the real astonishment is the carbon dioxide. Or the parent star itself may have radiated energy differently, processing ices in ways our Sun never could. Planetary migration within that system might also have stirred the disk, mixing hot and cold materials in unexpected combinations. Then there is cyanide, the molecule that lends many comets their ghostly green hue. In Atlas, cyanide emissions rose later than water, delayed in the warming sequence. On our comets, the two appear together because their ices evaporate at similar temperatures. That delay hints that Atlas's cyanide may be locked inside sturdier compounds, organic cages, that need extra heat to break open. And of course, there is nickel glowing without iron, the solitary metal still teasing chemists with its refusal to behave. Every element Atlas releases is a clue to its birth conditions, its temperature, its pressure, the alchemy of the nebula that shaped it. Whenever a comet carries both water and carbon-rich molecules, one question always follows. Could such objects spread the chemistry of life? The idea is called panspermia, that life, or at least its building blocks, might travel between stars on icy messengers like this. Atlas checks all the right chemical boxes. Water, organics, cyanide, all precursors to amino acids and nucleobases. If someone wanted to design a comet to deliver prebiotic ingredients to a young planet, it would look a lot like this. But speculation is not evidence. No living cells have ever been found in a comet, and the journey between stars is merciless. For millions of years, cosmic rays and ultraviolet light bombard interstellar travelers, shredding complex molecules. DNA, proteins, even simple amino acids would not survive unless buried beneath meters of protective ice and rock. What might survive are chemical fossils, stable molecules forged long ago in another system, perhaps on the surface of an ancient planet or within its atmosphere, later trapped in ice and launched into space. If those molecules endure, they could tell us stories no telescope can. Tales of alien atmospheres, of extinct metabolisms, of chemical pathways that life once explored elsewhere. That is why some scientists dream of meeting one of these travelers up close, not just observing from afar, but intercepting it. Imagine a spacecraft able to match velocity with an interstellar comet, to land, drill, and bring home a fragment of its alien chemistry. The challenge is enormous. Such objects race through space at tens of kilometers per second. To catch one would require a probe already waiting beyond the planets or capable of near-instant acceleration. But the reward, a sample from another star system, would be priceless. Direct evidence of how different the universe's recipes for worlds can be. Atlas is already racing away, far beyond our reach this time. Yet its brief visit has shown us what's possible. It has reminded us that the galaxy is not uniform. It's a mosaic of chemical experiments, each star system writing its own version of creation. Not all cosmic discoveries come from professional observatories. Sometimes the universe reveals itself to people simply willing to look. In 2019, radio astronomers stumbled upon vast circular structures glowing only at radio wavelengths, odd radio circles, or arcs. They appear as enormous rings, hundreds of thousands of light years across, invisible in optical light, yet unmistakable in radio maps. What causes them is still a mystery. Shock waves from massive black holes, galactic winds, or something we haven't imagined yet. Because they're so faint, algorithms often miss them. That's where human eyes make the difference. Through the Radio at Home Citizen Science Project, volunteers across the world scan radio images, flagging anything that looks unusual. They're not told what to find, they're told to look for weird. In March 2025, one volunteer spotted a spectacular anomaly. Two overlapping rings forming a figure-8 pattern, the most distant and energetic orc ever recorded. The discovery came not from an automated search, but from a person staring at data and thinking, that doesn't belong. Projects like these rely on the Low-Frequency Array Network, a continent-spanning radio telescope that produces data far too vast for professionals to check manually. Automated pipelines sift through it, but humans remain the ultimate pattern detectors. Time and again, volunteers have uncovered structures, algorithms, ignored a ring surrounding a distant galaxy, a jet ending in a perfect halo, a shape that theory never predicted. It's a lesson that extends beyond radio astronomy. The new Vera Rubin Observatory will soon generate 15 terabytes of data every night for a decade. No team, human or machine, can review it all alone. The future of discovery belongs to cooperation, machines for speed, humans for curiosity. Could a citizen scientist have noticed 3I Atlas's anomalies before the professionals did? Possibly. Its spectral data are public. A trained eye might have seen that nickel without iron signature, or its impossible early activity. The key word is trained. Citizen science is powerful, but it isn't friction-free. Opening data to everyone means opening it also to mistakes, to misinterpretations, to conspiracy theories that see alien intent in every flicker. Professional astronomers know the cost of false positives. Each candidate object must be verified, cross-checked, peer-reviewed. That takes time, expertise, and limited telescope hours. When amateurs flag hundreds of questionable signals, fatigue sets in. Skepticism grows. Yet shutting the gates would mean losing genuine discoveries. The solution isn't exclusion, it's education. Projects now build training pipelines, teaching volunteers how to recognize artifacts and estimate uncertainty. Mentorship networks connect experienced amateurs with newcomers. Many initiatives require multiple independent confirmations before an object is elevated for professional follow-up. Such systems filter noise without dimming enthusiasm, and the payoff is immense. A global network of curious minds scanning the heavens, catching what no algorithm was built to find. Could someone like that have noticed Atlas's superlinear brightening early on? Perhaps. Amateurs already contribute to Comet monitoring, recording brightness curves night after night. With guidance, they might someday detect the next interstellar wanderer before the headlines do. This partnership between precision and passion, data and imagination, is becoming the backbone of modern astronomy. Machines can measure, but only humans can wonder. And in that wonder lies progress. It's not hard to imagine how this could have played out. A volunteer staring at a light curve might have said, "This isn't behaving like a normal comet," days before a formal survey flagged it. We've seen this pattern before. Planet Hunters-style projects have helped push the transit method forward, spotting exoplanets by those whisper small dips in starlight across Kepler's archive. Amateurs routinely pick off near-Earth asteroids that slip past automated filters. And when a nova erupts, it's often backyard observers who ring the bell first because they're out there every clear night, while major facilities are booked months ahead. The point isn't to replace professionals with hobbyists, far from it. October 2025 gave skywatchers a photogenic stack of events. Mercury climbed into a bright evening apparition. Ceres hit opposition, shining at its best. And in the background, our interstellar outlier 3I Atlas kept doing impossible things. Social feeds lit up. 3 dots connected into a story. Was there an alignment? A hidden resonance? Was the solar system somehow waking the comet? Short answer, no. Mercury's orbit doesn't drive outgassing on an interstellar body far from the Sun. Ceres's geometry relative to Earth has zero leverage on chemistry taking place billions of kilometers away. These are independent events, merely visible at the same time. But our brains are built to find patterns. Pattern spotting kept our ancestors alive: berries versus poison, tracks versus prey. That gift overshoots in the night sky. It's pareidolia at scale. Faces in clouds, voices in static, meaning in coincidences. History rhymes. In 1910, when Halley's Comet returned, chemists detected cyanogen in its tail. Headlines screamed poison. People bought masks. Some sealed their windows. The tail, of course, was a near vacuum. Nothing happened except panic, fueled by unrelated tremors in politics and nature that happened to coincide. We're watching the same psychology at work. Atlas is truly odd that part is real. Mercury and Ceres being well placed. Pure timing. Calculations are unambiguous. Mercury's mass and distance confer negligible gravity on an object in the outer system. Ceres contributes even less. Atlas's behavior comes from its own interior, solar radiation, and its composition, not from where a small planet happens to be. Why do conspiracies bloom anyway? Because stories feel safer than randomness. If the comet's activity maps onto planetary positions, the universe looks ordered. If not, then sometimes the cosmos just surprises us. That's uncomfortable. Confirmation bias then does the rest. We remember the hits and forget the countless nights when nothing lined up at all. Social media turbocharges this like mines cluster, screenshots multiply, and an alternative narrative acquires momentum. The antidote isn't cynicism, it's statistics. With thousands of celestial events in play, coincidences are inevitable, and they look meaningful even when they aren't. Keeping that in view helps us read anomalies like Atlas without turning them into myths. October 8th, 2025. Blue Origin's new Shepard NS-36. 6 passengers, 11 minutes, across the Kármán line and back. A mystery flyer kept private until touchdown, nothing unusual for a paying customer. On paper, it was routine. The company's 15th crewed hop. A few write-ups, some posts, and silence. That silence is what nags. No surge of clips. No trending cabin footage. No viral window views. Normally, Blue Origin floods the zone with imagery. Floating passengers, awe-on faces, Earth framed in black. This time, the coverage was so thin, the absence itself felt loud. It invites questions, some fair, some conspiratorial. Was the manifest as reported? Was the timeline real-time? Was older footage repackaged? Careful. These are paranoid paths, and yet they sprout in vacuums of information. Contrast with April 2025. Another new Shepard flight went hyper-viral, not for failure, but fame. Celebrities aboard. Millions watching. Within hours, social media turned forensic. Hair behavior in microgravity, hatch angles, window reflections, non-existent scorch marks, every frame circled and annotated. Experts debunked, as they do. Hair floats strangely when air currents, not gravity, rule. Hatches look different by angle and lighting. Dust can hide heat signatures. Optics distort. Debunking rarely ends the story. For believers, it reads as cover-up, and the loop tightens. Now stack these two flights. One drenched in attention and doubt, the next barely noticed. Which looks stranger? The loud one invites conspiracy. The quiet one breeds it. The broader lesson isn't about Blue Origin at all. It's about how mysteries metastasize online, how gaps get filled with narrative. In spaceflight, as in astronomy, transparency is ballast. Without it, speculation finds orbit. The cosmos throws curveballs. we swing with physics and with projection. Or Tabby's star, wild, irregular dimming that didn't repeat like a planet transit. Dust, comets, collisions. Someone half-jokingly wrote Dyson Swarm, and the idea stuck because it's audacious and because we're hungry. Odd radio circles, fast radio bursts. Now 3i Atlas each becomes a screen for our hopes and fears. Are we alone? Is there intention out there? This isn't stupidity, it's human wiring. Pattern bias leans toward false positives. Better to jump at a shadow than miss a predator. Add existential longing. We want the universe to wink back, so we push on anomalies until they confess to meaning. Atlas reflects that back at us. In its vivid green coma, we see our desire for wonder and the discipline science demands. Maybe one day something truly inexplicable forces a rewrite of physics or confirms company in the dark. Today, we have a comet deeply weird, probably natural, and that's already miraculous enough. Sometimes one washes up on our shore. Interstellar visitors are not alien as in intelligence. They're alien as in foreign chemistry. Each one is a data point from a different recipe of star, disk, temperature, and time. The outsiders don't. 2i Borisov, rich in carbon monoxide, familiar behavior, but with a gas-to-dust balance hinting at a colder nursery. 3i Atlas, water and carbon dioxide roaring at huge distances, nickel without iron, cyanide turning on late, a dialect we barely understand. 3 guests, 3 different chemistries. Extrapolate, and the diversity is staggering. In some systems, comets might be nitrogen ice heavy. In others, methane dominates. Around hotter stars, the snow line moves outward, changing what freezes and where. Disks stirred by migrating giants may mash warm and cold zones together, baking hybrid ices we've never catalogued. There are probably organics and crystalline oddities. A chemist would swoon over molecules that make perfect sense in conditions that simply don't exist here. Push the thought one step further. If life's prebiotic kit needs water, organics, nitrogen, phosphorus, sulfur, then many interstellar comets will be sterile couriers, lacking the ingredients to seed a world. Maybe most are. The universe is huge. Parameter space is larger. Nature tries everything, but not every try carries life's toolkit. And that, too, is data. Each sterile bottle tells us where the spark might not take hold, sharpening the search for where it could. That idea has a name, panspermia. Controversial. Yes. Unproven. Also yes. But the door is not closed. And 3i Atlas checks many boxes: water, carbon-rich molecules, cyanide as a prebiotic precursor. Not life, most likely, but the chemistry that can precede life if it lands gently on the right kind of world. Each interstellar visitor enlarges the sample set. We have 3 today. In a decade, we could have dozens. In half a century, hundreds. With every newcomer, we'll log composition, orbit, and activity, building statistics instead of anecdotes. Maybe we discover that water-rich comets are common everywhere, or that our system is the odd one out, and most stars make dry, carbon-loaded rubble. Either answer rewrites our expectations. And perhaps, just perhaps one day, a spectrum will reveal biomarkers that defy geology. Complex organics with handedness, phospholipids, isotopic ratios that whisper metabolism. We're not there yet. Atlas doesn't shout life. But it does carry information, and information is science's currency. Every interstellar object is a free sample delivered to our doorstep. All we have to do is look closely. Back to that stubborn anomaly. Nickel without iron isn't a party trick. It's a fingerprint. And fingerprints hint at where something has been. Stars are element foundries. Fusion in their cores climbs the ladder from hydrogen and helium to carbon, oxygen, silicon, iron. When the massive ones die as supernova, they mint even heavier elements, nickel among them, and fling them into space. Those ashes seed the next generation of stars and planets. But not every supernova leaves the same recipe. A Type Ia white dwarf detonation and a core collapse supernova don't imprint identical knife ratios. If Atlas formed from a cloud enriched by an unusual blend of supernova, its nickel to iron balance could be skewed from birth. Layer on the likelihood that Atlas comes from the thick disk, an older population with lower overall metallicity, and you have a plausible path to nickel bright, iron faint. Why does that matter? Because comets can be time capsules for galactic chemical evolution. We can take stellar spectra and tally metals, but we can't inspect long-dead stars. An interstellar comet that condensed from their ashes preserves a frozen archive of those conditions. If we could sample Atlas directly isotopes, trace metals, mineral phases, we'd literally hold a shard of another system's history. It would be like reading a chapter of the Milky Way written billions of years ago, thousands of light years away. There's a fringe speculation that occasionally surfaces. Could odd metal ratios trace technological processing industrial byproducts mixed into a debris disk, later baked into comets? If a civilization mined and refined metals, you might expect selective residues. To be clear, there's no evidence for that here. It's science fiction adjacent and rightly treated with skepticism. The simpler path points to chemistry and formation environment, organometallic carriers, fractionation during condensation, surface processing in interstellar radiation. Nature has many levers we haven't pulled yet. What excites researchers is the prospect of a catalog, a library of elemental barcodes from dozens, then hundreds of interstellar bodies. Map those barcodes against incoming directions and orbital classes, and patterns may emerge. Thick disk travelers versus inner disk visitors. Objects from the galactic center corridor versus the outer halo. Perhaps one region trends carbon-rich, another water-heavy. With enough entries, comets become tracers of the Milky Way's structure and history. Atlas is entry one. Its strange nickel is a reminder. Every ratio is a clue. Every clue a sentence in the galaxy's long autobiography. Not many, but enough to do statistics. Crunch the detection rates, sky coverage, and brightness biases, and a picture emerges. At any given moment, there are likely several interstellar objects inside Jupiter's orbit, small, dark, fast ghosting past our surveys. We catch a few by luck. One passes close, another brightens just so. A third wanders through a well-watched field. How many slip by? Dozens, hundreds, probably. Detection is hard, but it's about to get easier. Enter the Vera Rubin Observatory in Chile. Rubin will sweep the whole visible sky every few nights to extraordinary depths, flagging anything that moves or changes. Forecasts suggest it could spot an interstellar visitor every month or more. 10 years could yield 100 objects, enough to turn anecdotes into population studies. The square kilometer array will add radio sensitivity, catching molecular emissions that optical telescopes miss. Space-based UV and ER missions will net the dusty, the faint, and the obscured. Our net widens, the ghosts get edges. The solution is bold. Interceptor missions. Keep a spacecraft fueled and waiting in deep space. The moment an inbound interstellar object is confirmed, launch or divert, match velocity, rendezvous while it's still warm with sunlight. Drill, sniff, sample. Maybe it was just chemistry, frozen gases, ordinary physics, nothing more. But to us, it was a mirror. It reminded us that even when we think we've mapped it all, The cosmos still hides poetry inside the numbers. And so we end where we began. A comet breathing in the cold. A world watching in awe. A question hanging between them, eternal, unanswerable, and beautiful. Because in the end, that's what science really is. Not certainty, but the courage to keep asking. Somewhere out there, a voice once said, something incredible is waiting to be known. And tonight, as 3i Atlas fades back into the dark, maybe it's whispering the same thing. Keep watching. Keep wondering. I was never the last.